You are looking at a 500-ton steel giant, buried deep inside a concrete fortress, spinning at terrifying speeds. And the raw, violent rotation of this machine is doing exactly one thing right now, pushing electricity straight to the outlet you're using to watch this video. To understand how it works, we have to pull back from the machine and look at the structure that feeds it. A hydroelectric dam is essentially a man-made mountain, engineered to hold back an almost unimaginable weight of water. This diagram shows a cross-section of the dam and the reservoir behind it. The water sitting in that artificial lake acts exactly like a giant liquid battery. Every drop of water held up high contains stored gravitational potential energy. The distance from the surface of that water down to where it's released is called the head. The higher the head, the more pressure builds up, and the more energy is banked, waiting to be unleashed. By wedging this wall into a valley, engineers hit pause on the natural water cycle. They intercept the rain and rivers driven by the sun, capturing all that gravitational work to create a massive, stable reserve of energy on demand. When a city needs that stored power, operators open massive gates deep underwater. The crushing weight of the lake above forces the deep water into enormous enclosed steel pipes called penstocks. This tracks the water's path down the dam. Plunging down the steep penstock, it accelerates to over 60 miles per hour. Reaching the bottom, it's funneled into a tight space. The stored potential energy is converted into pure kinetic energy, a focused, high-pressure jet. That high-speed jet is aimed directly at a Francis turbine. It looks like a complex bladed disc, precisely engineered with curved stainless steel blades that intercept the rushing water from every possible angle. The jet slams into the metal. The blades catch that immense forward force, transferring momentum into the heavy steel structure, forcing a rapid spin. The water's job is done, and it flows out to rejoin the river. But that brutal collision has completed the next energy conversion. The downward, rushing pull of gravity is now pure, rotational mechanical energy. That violent rotation travels straight up a thick steel shaft into the powerhouse, arriving at the generator room. The central spinning piece is the rotor, a heavy electromagnet weighing over 500 tons. It rotates inside the stator, a stationary cylinder lined with thousands of feet of tightly wound copper wire. The gap between them is often just inches. This illustrates electromagnetic induction. As the massive rotor spins, its powerful magnetic fields sweep past the stationary copper coils. This moving field excites the electrons naturally sitting inside the copper wire, pushing them forward into a steady flow. That flow is an electric current. But the electricity leaving this room is at a relatively low voltage. If you tried to send it hundreds of miles to a city as is, most of the power would just burn off as heat along the wires. To survive the journey, the electricity passes through a transformer. It steps up the voltage, increasing the electrical pressure so current can travel fast distances. From the switchyard, the power merges onto the superhighways of the electrical grid, the high-voltage transmission lines, carrying it across the landscape. After a final series of step-down transformers near your neighborhood, the mechanical spin of the river has been successfully translated into an invisible, high-pressure flow of electrons, engineered to safely enter your home. This graph illustrates one of hydropower's most crucial benefits to the grid. Unlike solar panels or wind turbines that rely on the weather, a dam is highly dispatchable. When millions of people get home from work and turn on their air conditioners, creating a massive spike in demand, operators can open the gates and have megawatts of power online in minutes. But commanding that level of instant energy exacts a heavy toll. Building the reservoir requires flooding vast valleys, which displaces communities and permanently submerges natural ecosystems. The dam itself creates a physical barricade that severs natural fish migration routes. We build extensive concrete workarounds like fish ladders to help marine life bypass the wall, but the disruption to local populations remains severe. Downstream, the riverbed starves because the dam traps vital sediments in the lake, and the water released from the bottom of the reservoir is often unnaturally cold and stripped of oxygen, making it difficult for native species to survive. Because the entire system relies on the natural water cycle, a severe, prolonged drought can drop the reservoir levels so low that a multi-billion-dollar megadam can't generate any power at all. The electricity powering your device right now is the result of a precise split-second symphony of physics, gravity, and colossal engineering. It is an incredibly reliable tool, but one that demands a profound compromise with the natural world. This is just one piece of the massive infrastructure running our lives. What giant machine should we deconstruct next? A nuclear reactor? A container ship? Let us know in the comments and subscribe to see it when it drops. Thanks for watching.